Right. So the topic on this particular video is the idea of measurement, determining quantities of different items. And when you make measurements, it can be of lengths, it can be of volumes, can be of voltages, any host of them. And there are certain guidelines or issues that show up with measurement. Now, when it comes to measurement, as Wyatt Earp would say, accuracy in one's measurement is rather relevant, or in fact, you may wind up on the wrong side of a bullet. So let's take a look now at what this is about. First of all, measurements have units associated with them. And as we saw in the previous videos, there are different units for the same uh, area. For example, if you want to measure lengths, there is a cubit, there's a span, there's a fathom, there's a hand's breadth, there's feet, there's yards. These are all units that are addressing the same quantity, which we call length. Now, when you make measurements, there's always a certain amount of uncertainty or error. One expression that's often used is measure twice, cut once. What that simply means is there's going to be errors made in the measurement of, say, the length of a piece of wood you want to cut. Once you cut it, that's all you get. And since there's always errors in the measurement, you might as well measure it twice to make sure you got it right. So there's always error or uncertainty with measurements that are made. And there are levels of errors or levels of uncertainty that one can make. If, for example, you're using the length of your actual foot that's in your shoe right now, the level of accuracy you can get with that unit or that measuring instrument, the shoe length, is probably not as accurate as if you used a laser system that lets you measure distances much more accurately. So the types of instruments and stuff like that affects the level of uncertainty or measure of error. Now here's a simple reminder that we had discussed before. Any given instrument has divisions within it that divides the unit, in this case its volume, into smaller units. And you need to write down the measurement as accurately as you can, but you cannot exceed the accuracy that the instrument is capable of doing. In addition, you don't want to shortchange yourself. So you can see here on this graduated cylinder that measures volumes, you have a value that sits somewhere between 5 milliliters and 6 milliliters. And one thing that you always have to determine is what is the incremental difference in between those measurements. And so the only way to do it is to recognize you have a 5 and a 6, therefore that difference is a 1 milliliter. And the increments, if you count them, you'll notice that there are 10 incremental spaces. Therefore, the increment is 0.1 in between. In any kind of instrument, you always have to determine that by seeing what the values are and determining the increment. It's almost never written as to how accurate it is. So you have to maximize its ability. The last digit is the one that is not certain, so it's referred to as the uncertainty or estimated value. And always make sure you include your units. In this class on exams, if you do not include the units that are involved in the number, you will always lose a point and you can't get it back. So always know what those numbers represent. So a second reminder about using of instrumentation is you will notice that in this case there's a ruler down below, 1, 2, 3, 4, 5. In this case we don't give you the units, it's just incremental numbers. And you'll notice that there's this object, this green board, let's say, and you want to measure it. What you cannot do is you cannot write the number as 4.81950 centimeters. That is a level of accuracy. That's a level to which you're measuring that far exceeds the instrument. So the rule is you cannot record a value that is greater in accuracy than the instrument itself. How does that work? Well, in this case, that number is way too accurate, and you can only estimate one level of precision beyond the marking. Now, what does that mean? It means that right there, that's a marking. It's 4.5. It sits between the 5 value, and what happens is you can estimate one value. So you'll notice that the 4.8 is an estimated separation between 4.5 and 5. Again, that's the actual numbers written. Therefore, you can actually get to a 4.8. Now, when you have a volume, what you arrive at is a meniscus, and the meniscus is caused by the water or liquid riding up the sides of the container due to what's called capillary action, an idea actually we'll look at in this course. And so you always read the bottom of the meniscus or the bottom of the curvature. And so the question is, what would you write down as the volume measurement for this arrangement? And the answer is you would write it down as 36.3. Now, how did you get that? Well, first of all, you'll notice that the large marker is 35, and the next large marker is 40. So obviously it's a change in 5. Now let's count the smaller lines. 1, 2, 3, 4, 5. Okay, so the small increments between 35 and 40, the small increments is 1 milliliter. Now you'll notice that the actual meniscus sits between the first line and the second line. Therefore, the volume is 36 plus an additional amount, and you're allowed to estimate that last value. Now, as we've been discussing, there's always an error involved in a measurement. And what that error means is either you blew it as a person making the measurement, or there's always a limit to how accurate the instrument itself can be. And because of that, we need to explore the issue of this error. And there's two sources of it. The first one is what we just discussed, which is there's a limit to how sensitive or how accurate the instrument itself is, and there also is the technique being used by the person making the measurement, and there's errors that are possible there. Now, recognizing these two sources, the actual measurement errors fall into two groupings. The first group is called the systematic error. And the way to think about that is the instrument itself has a problem. The markings are not accurate. They're rubbed off. Or the springs of the scale are thrown off. And the result is the instrument itself cannot make good measurements because basically it's broken. And so every time you make a measurement with that instrument, it's always giving you the wrong answer because the instrument itself doesn't work properly. That kind of error is referred to as systematic. Now, a random error is usually caused by humans. If you're weighing out a certain amount of flour and you're casual about reading that amount or having a clean tray that you're using, or you simply are not paying attention and don't let the scale get to its proper location. So random errors are simply errors introduced by the human from when you make those mistakes. So here's the best way to illustrate that. First, what is a systematic versus random error? Well, if we were shooting arrows at this target, what would a systematic error look like? The answer is that one. Notice the person shooting the arrows always gets it around the proper grouping, but the actual bullseye is missed every time. In this case, for example, if you're shooting the arrow and you're using a sighting system, there's something wrong with the sighting system, meaning you're aiming according to your setup. The aim is at the target in the bullseye, but there's something wrong with it, and it's always directed in the wrong direction. That's a systematic error. It's a problem with the actual instrument. Now, what does random errors look like? Random errors simply are human error. You weren't paying attention for one of the shots. You dropped your elbow, let's say, and caused a different shot to drop low. Occasionally, you get kind of close to the bullseye, and so you see tremendous scatter in the random errors. There's no pattern to it, whereas a systematic error, there's nice close clustering or grouping of your target shooting, but it just doesn't come close to the actual bullseye. So again, the systematic is the imperfection in the equipment, and the random errors are limitations in the equipment itself or in the technique itself. So let's take a look at issues associated with accuracy versus precision. Now this is the second idea associated with the measurement system. And what you have is the following. Accuracy is referred to how close did you get to the actual value, the true standard value. For example, we'll be doing a lab studying heat. And when you do heat, there's a property of an object called specific heat capacity. Now, the specific heat capacity value of a substance is known. And so there is a standard or accepted value known about the specific heat capacity of, say, aluminum. When you do this lab, you're going to be asked to figure out what is your specific capacity of aluminum, and how close you get to the accepted value is referred to as how accurate did you do the lab. Now, precision is how much can you make each measurement made be like the other. How consistent are you? So there's a clustering of the value or measurements that you make. Now you can put these two areas into a nice grid. In this grid, what you see is the arrows being shot. They're not very precise. They're imprecise. How come? Because you'll notice that the arrow shots are scattered everywhere. Clearly the shooter wasn't paying attention or did it correctly after each shot, and it randomly occurs. Now, it's also considered inaccurate, and that's because your shots in general missed the target, missed the bullseye. And so when you see data scattered in the manner we're looking at, we would say it's imprecise, and we also would say it's not accurate. In this case, what you see is you see good precision. What that means is there's good clustering of all your data. Every number seems close to the other number. However, the numbers you are getting are not near the actual value. So in this case, there is an error usually associated with the instrument. There is something wrong with the instrument. It keeps giving you the wrong value. And if we keep going on this, we can see that this one is actually somewhat accurate. The accuracy is because the shots hover around the bullseye area, but they're very scattered, and so it's imprecise. And of course, this is the ideal situation, which it is both precise, which means that your data is clustered, and it also is accurate, meaning it actually, those numbers show up fairly close to the accepted or true value. So measurements are both precise or imprecise, and they're accurate or inaccurate. And those two ideas together make up your overall value. Now this, of course, is the brother being on purpose very inaccurate. and also imprecise. So let's take a look. Precision allows you to get the numbers to very, very close values. And it depends upon the degree of precision that the instrument itself has. So in this case, I'd like you to take a moment. You can pause the video right here. I would like you to list the arrows, the rulers here in increasing precision, meaning that the instrument that is least precise goes first, and the ruler with the greatest precision last. So pause it for a moment, take a look, list it, and see if you can get your answers correct. And there we go. You'll notice that B is the least precise because it has the least number of intervals, if you will, or the least gap in the intervals as an instrument. You could take it all the way down to C, which will have the greatest precision. It is an instrument that has greatest ability to measure the length of an object. Naturally, through the centuries, instrumentation has become more and more precise as the technology to make these measurements get greater and greater. And again, bear in mind that these rules of precision apply to any kind of measurement. So there's precision in length, there's precision in weight, there's precision in voltage, there's precision in luminosity. So these ideas do not relate to a particular type of measurement, but to all measurements. Now in this case, would you call that precise or accurate? Bummer. Let's put that on instant replay. What do you say? Not good. So